The main reason people don't like it is just because they feel like it is too bizarre to be true. You only ever see it either going this way or going that way. But we know from theory that it's doing both things at the same time. There are other versions of us, but it's not that much stranger than, like, say, anything that happens in general relativity. I would like to defend it and also use it to do other stuff with. There are situations in which it matters that you prefer, for example, Everett over other theories. The assumptions are very simple. So we don't really put the universes in there by hand, they just appear. You have fewer assumptions, you don't need the collapse postulate. A measuring apparatus is made of atoms. So presumably whatever it's doing should be described by quantum theory. When we meet up, there are rules for which versions of us can see the other ones. There are different versions of this podcast.
Do you really believe it? Hello, welcome back to the Quantum Foundations podcast. I'm Maria Villaris. I'm finishing a PhD in Quantum Foundations at the University of Oxford. And today I'm joined by Sam Kuypers. Sam used to be a PhD student in my group with Vladimir Vedra back in Oxford, but now he's a postdoc here in Montreal at the University of Montreal. He's in the group of Gilles Bressard, working on quantum foundations. And today we're going to be talking about the many worlds theory of quantum mechanics, which relates to Sam's research from his PhD and ongoing work. So thanks for joining us, Sam.
Thanks for having me. It's great fun.
And just to let our viewers know, we're in a change of scene now. We've gone on tour from our usual Oxford location to Montreal for this episode. So enjoy the new setting of the podcast on tour. So to get started, could you just tell us a bit about how you ended up doing research in quantum foundations and ideas relating to many worlds?
I think it all started when I read, it must have been Fabric of Reality back in something like 2016. Uh-huh. And I was very interested in everything in the book, but the thing that I was most skeptical about while reading it for the first time was actually the chapter about quantum theory. So the book is various sections, and it's about quantum theory, about computation, about evolution. Mm-hmm. And the thing which I found most intriguing, but the thing that I really wanted to see some detail about was the chapter about the many worlds interpretation of quantum theory, because I thought it was such a strong claim to make. So then I actually ended up reading Everett's thesis about the topic while I was doing my master's, and then I was just kind of hooked. I was like, wait, this might be true, and if it is true, then why didn't I know about it? Why didn't I study it before? And it made sense of lots of things in quantum theory that I either hadn't really seriously contemplated at the time, or which I thought were strange, but just did not know how to solve before coming across the theory. So then, from there on, I was interested in foundations and found a way of doing my PhD about it. That's kind of how my interest in the topic got started initially. Yeah.
Mm-hmm. Cool. It's always nice to hear what particular work or content started the interest. So yeah, that's interesting to know. Cool. Great. So the aim of this episode of the podcast, so the podcast has two parts. We have a part that's aimed to be accessible for anyone who's interested in the topic, and another part which is aimed at people that have an introduction to quantum mechanics already, and then that's the mathematical part that can kind of explain things in mathematical detail for people with that background. But today we're going to be talking about many worlds on a more accessible level, but still a deep, hopefully deep conceptual discussion about what's really going on with the many worlds theory. So to get started Could you tell us a bit about what the many worlds theory is, and maybe a bit about what's the problem in general that interpretations of quantum mechanics are trying to solve? Why are we even talking about interpretations of quantum mechanics?
Yes, so the way I tend to think about all of this is that there are two dynamical processes in quantum theory which both seem necessary. One of them is unitary evolution, which is the kind of evolution that you see when systems are not being observed. So it's Schrödinger equation type evolution. It's the evolution of things, of systems, just not in the most general situation, but in fairly general situations. And then...
So unobserved evolution.
Yeah.
According to the laws of quantum mechanics, they say when it's unobserved, this is what's going to happen.
Yes. Mm-hmm. Yeah, you could even say that it's evolution of closed systems. Mm-hmm. And then, of course, there's also open systems, but typically you can model them as being part of larger closed systems, so that way the unitary evolution explains that as well.
Yeah, so open system has... So closed system is just something isolated from everything else. Open system, we have something else interacting with it, but then we just zoom out, include the thing that we're interacting with, and then we've got a closed system again. So you can always zoom out to include whatever your system's interacting with as being part of your overall system.
Yes, yeah, like if you're on Earth, there's energy coming into the Earth or onto the Earth's surface through the sun. So the Earth's surface on its own is not a closed system, but if you include the sun as well, then there's to high approximation, there's no energy coming into the system, into the solar system. Even that's not quite true, but it's maybe a good way of thinking about it. That you can, as you said, you expand the system that you're considering to also include whatever is influencing it. Like the surface of the Earth is being influenced by the sun, so if you include the sun, then the system as a whole can be considered closed. But anyway, so there's a way in which systems evolve in quantum theory, which seems to be quite fundamental. That's really the main thing. And then there's another way in which systems evolve when they're being measured, and that in itself is really quite odd. That there should be such a thing as the way a system evolves when it's being measured. That it raises the question of what does it mean for a system to be measured? When do these measurements happen? Can you make that happen by only by people? Do they happen because of other things like what is a measuring apparatus? Can the environment be a measuring apparatus? Can very small systems be measuring apparati? Where is the cutoff for this kind of thing? And they're kind of in tension with one another, these two ways in which systems evolve. And what the many worlds here says is, well, there's really only one way in which systems evolve, and that's unitary evolution. And we can use that to explain the second type, so that we've essentially cut down on our assumptions. So we've are able to explain all the same things while making fewer assumptions, and therefore we have a better explanation. That's roughly, like in a nutshell, that's how I would summarize it.
So there's the evolution of closed systems is this unitary evolution, which means reversible evolution according to this Schrödinger equation law of quantum systems evolving. And then you have the other evolution is the one with the measurements. That's kind of weird. Why do we have these two different types of evolution? And then you're saying Many Worlds says actually we just have the first type.
Yes. Yeah, so that way you can it resolves lots of these issues that I just mentioned, like what is a measuring apparatus and what is what counts as a measurement, because then you actually have a theory of what measurement is within quantum mechanics. So you have a theory of measuring devices, or measurers for short, which is a quantum theory. So another way to think about it is a measuring apparatus is made of atoms. So presumably whatever it's doing should be described by quantum theory, and that again is kind of the same conclusion follows, that you have a theory of how measuring apparatus behaves in a unitary way, and when you have that theory, again, you no longer need the second postulate. You can kind of get it out of your theory of the measuring apparatus and what it is doing when it's measuring a system.
So any situation where we have a measurement device, whether it's a detector of photons or a human looking at something, or any other measurement device examples. Anything that's like does a click of some kind.
It's noteworthy that lots of measuring apparatus, the measuring devices, are very different systems from one another. So that's another thing where it's not, here is this one system which always does the measurement. There's an explanation of what the various different systems that we use as devices are doing and how they are alike. So, like a cloud chamber is also a measuring apparatus, and you can use it to measure the trajectory of a particle. And that's a very different thing from something like the Stern-Gerlach experiment or from the Mach-Zehnder. But they all have things in common, which intuitively we know that they do. Intuitively we know all these things are somehow performing a measurement because they're telling us about the position or the magnetization of particles and things involved in them. But there's the question of, well, why are they all, what do they have in common, right? So again, that you need a theory of what a measurement is so that you can connect all those things. And I think Everett or Manuel's interpretation, or I tend to prefer the term Everettian quantum theory or just quantum theory nowadays, because it's interpretation is already, I think, almost misleading. It's almost misleading to talk about the interpretations of quantum theory. I mean, maybe we can come back to that, but it's the thing which Everettian quantum mechanics offers is an explanation that unifies these various different things with one another. Because what's really happening in each of these situations is that the measuring instrument is gaining some information about attributes of other physical systems, which introduces the idea of information into physics and things like that. And it's also, maybe in hindsight, unsurprising that the kind of Everettian considerations and thought experiments led to something like quantum computation, because information is clearly an important thing in measurement. So it kind of brings together lots of different separate ideas. That's a good point. So we have measurement devices that we're familiar with, but they're very different, implemented in very different ways. And then you're saying the unifying factor is that they all retrieve information about a system. That's the property that's unifying them, and that's the property that's about information. Yes.
It's not about the way that the cloud chamber is built, or the way that a photon detector is built, or the human eye, or anything.
Yes.
The unifying factor is information. And so, so can you expand on how the many worlds or Everettian theory solves this problem? So what happens when we just have these closed system laws of physics? How does that then apply to, how does that help us explain what these measurement devices are doing?
So I think I made you intentionally avoid the term interpretation there, or maybe not. I don't know. Anyway, So one of the unintuitive things, one of the reasons why we need this second type of dynamical process, the second type of how systems evolve, is that this thing which I'm sure you explained on the podcast, the systems can be in superposition, so like they can do two things at the same time. It can be particle takes two trajectories at the same time. It can be having two different spins at the same time, something like that. And the thing that happens during measurement is that we only see one of those possible outcomes. So maybe a simple one would be the path of a photon. So a photon comes into a beam splitter, comes in, hits the beam splitter, and then splits in two.
Yeah, so beam splitter, highly reflect, well,
yeah, it's like a silver mirror.
Yeah, half silvered mirror that puts it into a superposition of reflect. Photon hits it, and then it ends up in a superposition of being transmitted and reflected.
Yes, yeah, exactly. So it's only going two places at once. And the weird thing is that we only ever see it in one of those locations. So if we measure it after the beam splitter, so it comes in, as you said, and splits in two, you only ever see it either going this way or going that way. But we know from theory that it's doing both things at the same time. Because, for example, we can make them re-interfere in such a way that wouldn't make sense if they weren't really doing both things at the same time.
Yeah, so we put another beam splitter, reflect them to meet at that beam splitter, and then because of interference there, they end up merging into one, and then we know that they went down both paths, because if they only went down one path, they wouldn't re-interfere and always come out in the same direction. So this is the Mach-Zehnder interferometer, if you want to look it up further. Yeah.
Yes. Yeah, so we just generally we have these things, interference experiments, which this is one of, and which would show that really the system is doing two things at once. It's being in two different states at once. But we only ever see one of those states. So if we want to measure is the photon here or there, then the thing that we always see is it is either here or there. We never actually see it doing both of those things at the same time. But the equations for quantum theory don't really say that. They just say, well, the system is doing both things at once, and then you need some extra postulate to somehow get definite outcomes. So you need to say, well, okay, if I measure the photon's position along one of these two trajectories that it's taking at the same time, I only see one of them.
Yeah, so that's kind of brought in. Like, we have the equations saying it goes down both at once, then we're like, oh, but we only see one. Okay, let's add this postulate that says we only see one when we look at it.
Yes.
Kind of thing.
Yeah, it's like ad hoc, as you're kind of putting it, it's an ad hoc thing. It is what we see, so somehow the equations of quantum theory should reflect that. And so it's put in by hand that with some probability you see one of these two outcomes happening. And so that was my first part of the answer. And the question was, how does the many worlds interpretation of the Everettian, I should be consistent myself. I can't switch now.
Okay, we will use these terms interchangeably. Everett. Okay.
Yeah,
what are the options?
Yeah, what's different flavors?
Many worlds interpretation, many worlds theory, Everettian quantum theory. I would have just used quantum theory because I feel like that's too controversial. Yeah, anything with Everett or multiverse, we're referring to the same kind of thing.
Yes.
Yeah, just use whatever you like.
Yeah, from now on, it doesn't matter what we say.
Yeah.
Still try to be consistent. But anyway. So the question is, how can you give an explanation of that happening? Because it seems like you kind of have to put it in by hand.
Yeah.
And the thing which Everettian quantum theory does is say, it's not just that the thing that you're measuring is in a superposition before you measure it. So it's not just that the photon is taking both paths at the same time, for example. It is also that when you interact with it, you do it in such a way that you register one of these outcomes, but you yourself end up in such a superposition. So you see the photon going that way in one universe, and you see it going up in another universe, but both of them exist at the same time, just that the photon itself was really taking both of those paths at the same time. So you can see, for example, how that would be reversible. So you alluded to the fact that the kind of the more fundamental Schrödinger type evolution, unitary evolution, is reversible, and the thing which we then mentioned, the collapse, is not reversible because you see specific outcomes in a probabilistic way. So there's no way of reversing that. In this picture, in this explanation, the whole thing is reversible because everything unitarily evolves from the initial superposition and you, the observer, being ready to observe the outcome of the experiment, to one in which you see one outcome in each of the universes. In such a way that you could also potentially undo it. For example, you could erase your memory of having observed the particle or the photon, and then you would be in the initial situation again.
Yes, this is a key difference between the picture you said before of having one type of evolution for the closed system, another type of evolution for measurements, saying that the closed system evolution applies to everything is very different because it's a case where everything is now reversible, because these reversible closed system equations now apply to everything, including the measurement devices, whereas before, when this measurement dynamics was brought in, that was this irreversible collapse. So it's a very, very different laws of physics at play here when we say that these closed system equations are now applying to everything. And practically, like you said in this example, even though when the observer looks at this photon, they'd only see one of them, in both cases, whether we have these measurement dynamics or closed system unitary dynamics, it's still very different because in the many worlds case, that could all be reversed back into into a single world again, where they've not done that measurement, or that measurement's been reversed.
Yeah, because it's a fully deterministic theory in that way. Like we in the collapse, if you have to use the collapse postulate, then you said you have to use some kind of irreversible probabilistic process, which somehow ends up in you seeing one of these two outcomes. And the explanation for why you only see one of them is, well, you happen to be the version, like in Everettian quantum theory, the reason is you just happen to be the version that saw that particular outcome, and you don't see the full system anymore. Like there's stuff in the world that's now hidden from view, namely the other branch, the branch where you saw the other outcome. You know, when we interact with that, it's not something you can see anymore. So it kind of looks like the world is behaving in a way that it shouldn't, because you can't see everything that's happening. Like, so the dynamical process appears to be something like collapse, and which is why you can explain it using only the unitary part of the theory. But that's because we have a very parochial viewpoint of the world. We only see a very small part of it, whereas the system as a whole is much larger. There's other versions of you in the experiment, and they're seeing other things. And if you see how all of them are behaving collectively, then the unitarity is restored. It just doesn't look like that to people living in it.
Yeah, and this is why it's called known as many worlds, is because you branch off into these two or multiple, it can be more than two, versions of yourself when you do a measurement. And so, yeah, they're kind of these worlds, but, and yeah, from the perspective of just one of them, you're not seeing everything that's happening in the globally. But like you said, these aren't like independent worlds that are just completely separate in the sense that it could be reversed again. So I guess that's why some people are not a fan of the many worlds words, because as a term, because it may be.
Yeah, I mean, it always. I think there's several ways in which maybe the terminology is slightly misleading. That'd be one of them, because you're right that they're never fully autonomous. They're only autonomous to a high degree of accuracy, and they're also not. They're not necessarily worlds in the sense that they contain everything in the universe, but we can get back to that as well later on. But so the terminology, in some subtle ways, might be a bit unsatisfactory. I still think that the main reason people don't like it is just because they feel like it is too bizarre to be true. It just can't be true. It would be too strange.
Yeah. It would be very strange. Because, just thinking about having all these different versions of yourself that have ended up doing different things, seeing different outcomes of measurements is very bizarre. So,
yes.
Do you really believe it?
As David sometimes says, I try not to believe stuff, but I think it's true. Yeah, it's not. It doesn't really matter if I believe it as such, but it's. Maybe that's too confusing a thing to say. But anyway, I think the theory is true. The theory is true, and it is our explanation of almost everything. Like, there's very little that you can explain with any depth that doesn't require quantum theory. And the main part of quantum theory that people use is really the unitary part. Like if you think about kind of the theory of superconductivity, body radiation, stuff like that, then really all of the explanation is in the unitary bit, and the collapse postulate is kind of just there so we can have predictions for measurement outcomes. I find it, how to put this, if you look at the other versions of what's supposedly going on, they're treated with much more leeway. Like wave particle duality is a thing which people talk about. Yeah. And that is a thing which we get taught and then we repeat it, and that's not seen as absurd. Wave particle duality, that's seen as totally fine. And many worlds is given a hard time that kind of gets away with it. And the weird thing is that the wave particle duality is in essence a contradiction. For example, something can't be both like a localized object and also a wave at the same time. Yeah. You can't explain anything with a contradiction. Yeah. So one of my responses is we have weird standards for which theories we're hard on. We give many worlds a very hard time, but we give we give theories which I think are clearly nonsensical a very easy time, like the wave particle duality theory. It is, as I said before, it is the fundamental theory of lots of very deep aspects of the world. And then it's a somewhat bizarre conclusion for ourselves, which is that there are other versions of us, but it's not that much stranger than, like, say, anything that happens in general relativity. General relativity is a really bizarre theory. It's a really bizarre claim to say space-time really curves, that time slows down. Yeah. That's it doesn't just slow down, it slows down in a way that's symmetric, so that if people are moving relative to each other, they both think that the other one the other clocks are running at a different rate than theirs. Like stuff like that is really bizarre, but it's fundamental physics. It works, and it works as an explanation, and it works really well. And the same is true of effort. So I have to. I wouldn't necessarily say I have to live with the conclusion, because I think it's kind of intriguing. It's not a curse.
You're not sad that you have to live,
It's not, I don't like. It's not like, oh, I'm really sad that, this conclusion might be true. But I wouldn't consider it that important either way, how I feel about the implications of it to me personally, I guess. Like, however the dice would have rolled on that, I would have just done, but I would have just thought about what is the fundamental physics in the situation.
Yeah. But I think some people find it so bizarre to imagine this myriad of other worlds that makes them think, okay, something's wrong, we haven't found the answer yet, we need to keep working on quantum theory. It's not right yet because it's so counterintuitive and absurd. But I guess that seems like a bad philosophy? Or is there something to the weirdness of it that needs more explaining?
But I think it's not really concerned with the physics of it, maybe. I mean, I would say that. But I sympathize in a way, because they think there's something wrong with the theory, and they want to have an explanation which they find satisfying.
Yeah.
I happen to disagree that is a thing which is wrong with the theory. But it's perfectly understandable that you might want to work on a possible alternative. It's not something that I find necessary myself, but I kind of sympathize. Yeah, it's like I can see you want to give it a try.
Yeah.
And undoubtedly, it can be interesting to see why it may or may not work, for example. But I just think it's a solved problem. It's like trying to figure out what's wrong with Newtonian mechanics. Like I would say, well, we know, and we have a theory about that, and we could always explore alternatives, but I think the one that we have is pretty good, and I would like to defend it, and also use it to do other stuff with. Because there are situations in which it matters that you prefer, for example, Everett over other theories. As to, I guess you should push back a little bit, but one thing I've noticed people say, and which in fact I asked ChatGPT at some point to give me like its strongest refutation of Everett, was that it doesn't comply with Occam's razor. So that's a version of what you're saying.
I hear people say that. Yeah. So they say that it's kind of bringing in too much baggage in a way to say that there's all these worlds and that's going to explain this measurement problem, because it's like, it's making the theory really seemingly unnecessarily big and complicated, I guess, by bringing in saying that all these worlds have to exist. It's like, yes. What's your response to that?
Well, the assumptions are very simple. So we don't really put the universes in there by hand; they just appear. They're not. It's not like we go, let's assume there's other universes, and then maybe we can explain stuff. What we really do is we say we find the collapse postulate unnecessary and problematic, and let's try to do away with it. So in that view, you have fewer assumptions. You don't need the collapse postulate, and you can still do quantum physics. and then the universes are a consequence of the fully unitary picture. So in terms of the assumptions, there's much fewer of them, and then the entities in the theory there's more of them, but they're cheap on assumption. Like there's not, we don't have to do any extra work to get them there, because we don't kind of, in a way you're kind of agnostic about them being there. You have the two assumptions, unitary evolution and collapse. You scrap the collapse, and then it so happens that you get these other universes in solving the problem.
Yeah. Yeah, so they emerge from the theory rather than being postulated as part of it. So then you're saying they shouldn't count as the thing that you're applying Occam's razor to, because they're a consequence of the simple theory. They're not a complex theory.
Yes. Yeah. Exactly. Yeah. We don't go saying this should really need some more universes. I think so there's only one of them.
Yeah,
should
not
have
enough universes here, and
yeah, exactly. Yeah, that's not you.
Yeah, and you think all of the universes are just as real as each other? The other versions of you and everything.
Yeah, fundamentally, there can only be like the multiverse, like everything that happens within it, everything that's in a superposition, everything that's entangled with one another, and that includes the many different versions or instances of you and me and everything around us, which is it is true that it is a truly staggering number. So, like every time a photon hits us, I think that basically causes a branching to happen. Wallace has an argument to that extent in his book, The Emergent Multiverse, and there's lots of photons hitting us every second. So there's lots of different branches already.
Yeah.
But at the same time, it is also that you would roughly expect to behave about the same in all of them. So the ways in which you're different in the different universes need not be very dramatic necessarily. I mean, there could be large changes, but many of the things that could happen to make like something like a branching event happen, like the photons that are constantly hitting us are doing that. Sounds a little bit dramatic called an event, a branching event, but to make branching happen, you don't need to do very much.
Yeah.
But that also means that the effects are not necessarily very noticeable. Like maybe in some universes, like a cup falls down off a table because of some random things that happened there, and in another universe it doesn't. And in both cases, my life is roughly the same.
Yeah.
So in both cases, you live roughly similar lives. I mean, there's going to be places where things are really, really weird and different just because of pure chance, but there's not the majority of them.
Right. Yeah. Yeah. It's not the norm that an event like a glass falling down off the table would drastically change your life, but occasionally it will, because it, I don't know, stops you answering some phone call that was life-changing, or you hurt your arm picking up the glass and then go to hospital and find out something crazy that
you meet the love of your life, who's the nurse who treats your finger, something like that. Yeah.
It's a good story for a rom-com or something.
Yeah.
Isn't Sliding Doors is kind of like that?
Yeah,
right?
I've not seen that movie yet. I've been meaning to watch it like forever.
Yeah.
I've seen the trailer, and the trailer is basically this, isn't it?
Yeah.
So it's like, you live slightly different lives, and then...
Yeah, and it's become a phrase of sliding doors moments, and the moments where there's something kind of random that has a big effect. But yeah, I mean, that's the intuition I have as well, is that in general, those kinds of things wouldn't affect your life overall very much.
Yeah, so occasionally they do, and of course, over time, there will be different you will have different lives in different branches. I would expect. So, like because over time there are these sliding door moments, as you call them, which is I like the phrase. You would expect that there are bits of the multiverse where you have a very different life. Like you met a famous actor, and then by chance, and then he invites you to become part of a movie that he's making, and something like that could happen somewhere. Almost. So weird stuff like that must happen somewhere. That's the other part of it. So it's two kind of two seemingly contradictory things are balanced out. So it's on the one hand, small changes don't usually matter that much, but also things which are very unlikely almost have to happen somewhere in the multiverse as well. So there are parts of it where you have a very different life. Like you might become a famous actress because you met this director guy who knows, you can kind of make up your own story for that. And that is a weird consequence. Like there's lots of philosophical issues which I think no one has really figured out here, to do with identity and personality and stuff like that, which I think the many worlds interpretation or Everettian quantum theory will have some things to say about. So I guess there are kind of philosophical issues here as well. Again, I don't think that would change my mind about physics. And if anything, I think the physics will help those questions be answered. But there are some, like, is the person who lives a very, very different life from you still you? In some sense they're not. They have a shared history, and how does that work? So there are questions that I don't really have answers to, but they do arise from these kinds of considerations.
So thinking about it as a physics theory, we've said some people kind of don't like it because it seems absurd, but there's a bunch of people that actually have physics problems with their theory, that they're taking it seriously and they're trying to take it seriously as a theory, and then they're pointing out things that seem dodgy about it. And one of the kind of big ones is the issue of probabilities, because when we actually do experiments we get probabilities. We have of a certain outcome when we measure a quantum system, and we have the Born rule, tells us what these probabilities are, and there's this objection of how can you derive a Born rule in the many worlds theory, since it's deterministic theory. There's some other issues of it we can maybe talk about later as well, but that one, I think in my experience, is the one that most people that are taking the theory seriously are worried about, the probability issue of, because I guess if I measure something and then there's now two versions of me both see that thing, then if one of them had 1/6 probability and the other had 5/6 probability, what does that even mean if we're both equally real and both seeing it?
Yes. So the one way I think about this is that there's a mix of deterministic aspect of the theory, which says that from a given initial state you are certain what the final state will be, including during measurements, and the apparent randomness that happens in quantum theory. And one reason for that is that you initially, so let's say you're about to perform a measurement, and you're looking at whether the photon goes this way or that way, knowing that it is really it's in superposition of those two states, so it's doing them at the same time and you will branch after measuring it. Then you know that one version of you will see the photon traveling this way, or let's put it like this way, and one will see it traveling that way. And there is no physical sense in which you can know which one of those you'll be, because both of those people at the end will have been you at the start. So both of them share an exactly identical past. So things which are exactly identical in every way become different during the experiment. That's a strange state to be in. It's and you can kind of see how something like probabilities would pop out of that. I mean, that's not a full answer, of course, but it's because they were both exactly identical for the experiment, they're I lost my train of thought just now. Is that approaching an answer? That was the best answer that I had ready.
Yeah, where do you get the vibe of probabilities? Yeah. So you said you have these, you have like these identical. Okay, so I guess working backwards, you have different versions of you that have seen different things.
Yes.
When they've done the measurement, but they have this shared history of they were completely identical before the measurement.
Yes.
And there's a randomness in the sense that before the measurement, you don't know which of these two you're going to end up being.
It's even worse, because it's not just that you don't know, is that there is nothing to know. Because there's no...
Because it hasn't happened yet, or what do you...
well, because it's not like there's a label that says this part of you will become the one that sees this outcome.
Right, so it's like it's not that you don't know which one you will become, it's that you can't know because you will become both. It's not like this experience of you will become the 0 one.
Yes.
It's this experience of you will become both individual experiences of each outcome.
Yeah, it's like that example David uses in the beginning of Infinity, where he says...
David Deutsch.
Yeah. David Deutsch. So David Deutsch uses this example in the beginning of Infinity, where he says...
which is his book, which is very good.
It's a good book. You should read it. You can imagine a digital bank account with $100 on it, and in a digital bank account there is only such a thing as there being $100 in the bank account. There are no individual dollars. They don't exist. There's only the number of there being 100. And you can then say, let's assume that maybe tomorrow I pay $50 to buy some dinner somewhere. And then I ask the question, okay, which of the $50 that was initially in the bank account was spent on dinner? And there's not really an answer to that, because there is only the fact that there were 100 of them, and the next day 50 of the 100 were spent on dinner. But you can't, even working back, you can't say, well, there were these ones. And that is also true in many worlds. Before the measurement, you are in some state, then you do the measurement, and there's then a version of you which sees one outcome, and a version of you which sees another outcome, but they had exactly the same initial state. There was nothing that distinguished them, and if you put the whole thing in reverse, then there is again nothing that distinguishes these completely identical versions of you before they become distinguished. So that is, it's weird how even with deterministic laws, like the bank account example always stumps me, because that's completely deterministic. You know for certain that 50 euros will be paid to, oh sorry, I made $, so $50 will be paid for dinner. And yet, if I ask you, so which of these $50 will be paid, then you can't say. There's no physics, there's no physical situation there. Like there's nothing to answer. There's just 50 of them, because there is only the fact of there being 100. So if you were, so to speak, if you were one of these $50 dollars, then something like apparently probabilistic is happening, because you don't know what will happen to you tomorrow. Even though the laws of physics in this little bank account example are completely deterministic, you don't know if you're going to be one of the 50 that will be spent or not, or if you will remain in the bank account. And that's very similar to the quantum one. So something probabilistic comes up there.
So we've got our $100 in the bank, and you said if we spend $50, you don't know whether you're going to be the $50 that's spent or not. This is a kind of nicely symmetrical situation where we're like, okay, there's a vibes of a 50-50 type chance of having been spent or not.
Yes.
What if it was like 70-30? What if $30 were spent? Can I now think in terms of probability, in terms of whether I'm one of the dollars that was spent? But I have a 30% chance of being spent.
I think you could say that, yes. And that is, I mean, the reason would be because that's basically how quantum theory works. And we know from quantum theory that you get these probabilities.
So how does that work in quantum theory? So let's say that instead of our 50-50 beam splitter, which splits our photon in an equal superposition, we have a 70-30 one. So there's 30% chance of being reflected, 70 being transmitted, and then we measure it. So there's still two versions of us, one that saw the reflected one, detected the reflected one that detected the transmitted one, and we know from our collapse postulate combined with Born rule telling us that that given this quantum state of the photon, when we measure it, we have this probability of 70% chance of seeing the transmitted one, so 30% chance of seeing the reflected one. How can I understand those probabilities using this kind of idea of the...
Yes.
Yeah.
Yeah, it's again like a bank account, because before the experiment, you don't know, and there is nothing to know about which version you will become. You're not labeled, they're not...
Yeah.
There's nothing yet that distinguishes each of the versions of you, and then as soon as you perform the measurement, some of the versions of you will have become the ones that see the photon going the one way with 30% probability, and the other ones will be the remaining 70% probability people.
But there was only one of me before, right?
Well, there is a measure, so maybe this is making it more complicated now, but it's so... I think there is in some sense an infinity number of you, but there is a measure of how many. So
it's kind of like the $100 is like, there's a kind of
an infinity
of small dollar measurements in there in
Yes.
a way.
Yeah, it's like there's infinitely many points in a meter,
Yeah.
and kind of in the same way, there is a measure on the number of universes, or a measure, or there is a measure that tells you how much of you is doing a particular thing. One of them means that all of you is doing one thing, and then a half means that a half of you is doing something, and a half of you is doing something else.
Mhm.
And I think it has to be that way because you can continually change this. So, like, it could be that during a measurement, some versions of me are seeing one outcome, but they're doing so gradually. So gradually, I'm changing from only having been in one state to going into another. Now that's a bit, that's a bit too complicated too. It's weird. So the probabilities clearly stumped me.
Okay, so let's. So there's a derivation of the Born rule, right? How can we derive the? Could you just summarize the approach to deriving this Born rule? How do we figure out what probabilities we should be seeing when we do a measurement?
Yes. So the way that Deutsch and Wallace derive it is by saying
David Deutsch and David Wallace.
Yes, lots of old Davids.
Lots of Davids. Yeah. And they did a derivation in 20 something. Together.
Yeah, I think that.
Or I guess Deutsch did it, and then Wallace developed it, and
yes.
Yeah.
Yeah, I think Deutsch did it in 1999, maybe earlier. Could be wrong about the date, and then Wallace somewhere in the 2000s, I would guess. And their approach was to say, imagine that we're playing a game using a quantum system. So you go to a casino, fictional casino, and then the slot machine that you use is not just a normal slot machine, it's a slot machine that uses a quantum state and gives you a completely random outcome. And the question here is, you believe in Everettian quantum theory, you don't know about probabilities, and how should you now place bets on the slot machine, or how should you, in these kinds of situations where there's a game with some kind of quantum randomness, how should you behave? And what they are able to do is to say, given very simple assumptions about how rational agents should behave in those situations, you can actually produce the Born rule. So you can produce what probabilities, you can get the probabilities from assuming the unitary part of quantum theory and simple assumptions about how agents behave, generally in situations where there is no probabilities. So it's kind of like, the nice thing about this is that in the classical theory of how agents behave, in classical decision theory, you usually do have that assumption of there being randomness, so you scrap that and just replace it with quantum theory. You just say quantum theory is true, we don't believe in these classical probabilities, so we just assume that they're not there, and then we keep all the other assumptions about how to make decisions. And it turns out that you can basically get the probabilities back in that way. So it's kind of like assuming quantum theory and the other assumptions of decision theory, you can get back what appears to be the classical kind of randomness. So you can get the probabilities in that way, except you still believe that quantum theory is unitary. So there's certain things which the decision maker will not believe, for example. So he doesn't believe the universe is inherently stochastic, which might be an assumption that you put in the classical decision theory.
Right. So if we derive the Born rule using this setting of someone placing bets and then reasoning that the way they should place bets is according to this rule, then why does it apply to all these? Like, it seems kind of strange that people should be involved, or someone having to decide something in a rational way should be involved. Because when I just have my detector and I'm checking for my photon clicks, no one's making a decision on what to do or how to place a bet there, right? So how can we reconcile that?
Well, you could be placing that. So that's one way of treating it. That if you were to place a bet,
Mm-hmm.
then, which you could do in that situation,
Mm-hmm.
then that's how you would get the Born rule out again.
Mm-hmm.
And it's by virtue of you being able to do that in all those situations. So you can always
Mm-hmm.
say, well, we could be placing bets on these things, and then we get these probabilities. If we were to do that, we can derive the probabilities.
Mm-hmm.
Then you get the probabilities in general from them.
So it's about the counterfactual possibility that you could have placed a bet.
I think so, yes.
Yeah.
I mean, it's also the case that you are still an agent, so you're still doing agency stuff. It's if you were to say, what are the probabilities for a rock?
Mm-hmm.
I don't really think there are those things. Like you still need the agent to get the probabilities out of quantum theory, and the agent's doing the measurement. So to me, it makes sense that it pops up there.
Mm-hmm.
The thing where we shouldn't want it to pop up is in other cases, like
when there's no agents.
Yes, exactly.
So if there was probability when there's just rocks, then we should be worried.
So for me to consider
because there's no possibility of having decisions there. Therefore, it would be very weird to have probability there. That's kind of what you're saying.
Yeah, exactly. Yeah. So that the agents performing measurements have probabilities. That makes sense to me. It's the other situations that would be weird.
Yeah. Yeah, I like that way of putting it, because it's kind of, reversing the question a bit. Oh, you told me, why do I need to explain all the cases of probabilities without agents? Then you're saying, well, probabilities with agents are the only cases where it makes sense. So if there was probabilities without agents anywhere, then you're worried about that. So
exactly.
Yeah. So why do you think everyone's still so worried about the probability problem if it was solved like 25 years ago?
Well, I don't know. I wish I knew. I mean, I don't know why people are not very persuaded about Everett anyway. I don't have a good explanation for that either.
Mm-hmm.
So it's like we're zooming in on a thing that I really don't really get. And then within Everett, why is everyone disagreeing about the probabilities? I'm not sure. Partly, maybe it's because there's so many different derivations and everyone likes their own version of it.
Mm-hmm.
And I as we discussed earlier, I don't really get why it's possible that there are various different derivations of the Born rule. So there, for the audience, I provided one, which is my preferred one.
Mm-hmm.
But there are others. Other people have very slightly different derivations of it, and they don't agree with one another on which one they like best.
Yeah. So the conversation we were having that Sam's referring to is that we were talking about the fact that there's all these different derivations of the Born rule from different many worlds people that are exploring the many worlds interpretation. They all have their own derivations, and somehow they've all derived the same rule from different assumptions. And so it kind of, I was kind of asking in this conversation, like, is there something, surely these assumptions have something in common, or they kind of can be turned into each other somehow, because it kind of seems weird that there's all these different ways of deriving the same rule. But I think it's not clear for any two given derivations what the connection, if any, is of their underlying assumptions. But
yes, but at least we can say that people who are worried that we can't derive from Born rule should not be worried, because we can derive it many different ways, maybe too many. The question is which one, which of the derivations of the Born rule should we like?
But that then worries people as well, because they're like, the many Wells people can't agree on, none of them can persuade each other of the right derivation of the Born rule, so it's still an open question. So you kind of have these,
yes, I do think that the decision theory argument is very persuasive. Like, it's not something that I've worked on myself, so, but having looked at the derivation of it, it feels very elegant. So that is something that I would like to say I've not seen in the other derivations, but it is a bunch of very elegant assumptions that use symmetry arguments and things like that to then get to exactly the thing that we're searching for, and it just pops out, and you can't really see where, if anywhere, there would be an error. So that's my little defense of the decision theoretic approach. I think that there will be some explanation for why there seem to be many different derivations of the Born rule. I feel like there will be some kind of overarching explanation that says, well, if you, the assumptions are roughly similar, like there is Carroll's derivation, which also uses similar symmetry arguments as the decision theoretic one does. And I feel like his is just a special case of the more general decision theoretic approach. So at least in that case, I kind of see why there would be two of them, just because one is kind of like a special version of the other. And then that's not so problematic, and I can imagine that some of the other approaches will be subsumed, or can be subsumed in the same way. And I mean, on the one hand, I kind of get that people would say that. Like, there's no consensus. It's just that for me, it was never really of that much concern, because the rest of the construction works. It's not like we have a great understanding of probability in physics anyway. Like, it's not like the classical understanding of probabilities makes much sense, because especially in classical physics, you get systems which behave deterministically, but we have stochastic theories of. And then how do you combine the stochastic element together with the deterministic one? And none of them can really do that. And definitely not in a way that's fundamental. So, the probabilities I think it's nice. I think the decision theoretic approach is nice. But it was never a thing which, to me, would have made me think that maybe the explanation of measurement was not correct.
You always seem less concerned about the probability thing than a lot of people are.
Maybe they think probabilities works really well. Which I never really had that sense that probability was an extremely well understood thing in and of itself, and now Everett is ruining it. It felt more like,
it's like, we can get probability in an elegant way in quantum theory.
Yes. Yeah. It's I think this is the thing that Deutsch has said at some point, but lots of the problems people have with Everett tend to be problems which already exist elsewhere in physics and are just, your attention is drawn to them by Everett, but it's not like the problem is worse than anywhere else in physics. It's usually much less worse, much less bad. So yeah, probabilities are a problem in lots of areas of physics.
Mm-hmm. Yeah. At this point in the podcast, we paused yesterday and decided to continue today. So we're going to pick up the discussion. So yesterday we were talking about how the problem of how to derive the Born rule and probabilities in the many worlds theory of quantum mechanics can be solved. And now we're going to talk about another technical problem with many worlds that worries lots of people, both historically and I think still causes debate today. And that is the preferred basis problem. So, Sam, could you tell us a bit about what the preferred basis problem is?
Yeah, so the problem is that there seems to be an ambiguity in theory, in the theory of measurement that Everett proposed, which does not exist in real laboratory experiments. So there seems to be something which in theory shouldn't be there, but is, because we don't actually observe this ambiguity in real life. And the ambiguity is as follows. It is that if you write down the measurement procedure in many worlds, then what seems to happen is you have a measuring device which measures things in superposition, and then it itself is in a superposition. But the superposition isn't a unique one. So you can say, well, look, the measured, for example, the position of a photon, and it seems like the theory would allow you to say, well, actually, if we write this slightly differently, then it didn't measure the position, it measured another attribute, and the measure recorded that perfectly instead of the position of the photon. Whereas if we look at what happens in a real experiment, then that doesn't seem to be the case. If you measure a photon, then you really definitely have measured its position, for example. You measure specific observables and not other ones. So that's in a nutshell, that's the problem, that there seems to be an ambiguity of which observable did I observe in the theory, whereas in practice you observed a definite one and not another.
Mm-hmm. Yeah, so in practice we always, whenever a measurement device measures some property of a system, it measures that property kind of by definition. It measures a property in practice.
Yes.
But if we write out the equation, the mathematical description of that measurement, and we can do this in this Everettian way, we treat the measurement device as quantum, we get this entanglement, and it's consistent with this thing we get in practice of this property being measured. But there's another way we could rewrite that mathematics, and it's fully consistent with something else having been the thing that was measured, a different property being the one that was measured. And now this seems kind of a problem because we now have our quantum equations are telling us it could be describing this having been measured, but it could be describing that having been measured, and in reality we just measure the one thing every time. Yeah,
so that is an ambiguity that shouldn't be there. The theory should not allow for that, or it should at least explain. I think it doesn't matter if it allows for it, but it should explain what is going on in real experiments and why we think that there is a definite measurement result for a specific observable. And so the name itself derives from the fact that there doesn't seem to be a preferred observable which has been measured. There seem to be many which have been measured at once. So that's the term. Preferred basis kind of comes from that. And the way I think it can be solved is through something called decoherence. So decoherence is another thing we might have to explain, I guess. It's a property where systems are, the general scheme is systems are interacting with an environment, and these interactions, they have a proclivity to do that, and it's difficult to prevent them from interacting with an environment.
Mm-hmm.
And it is these...
I guess linking back to the discussion about open and closed systems that we were talking about near the beginning of the podcast, we have our system is the system, environment is everything else, and this process happens when there is, this interaction between them.
Yes. Yeah, so there's some environment, and like it's can't think of a great example at the moment, but there is an environment to the system, for example, to the measurer, and it is, there's molecules of air that are hitting the measuring instrument, for example, and in effect, they are also kind of measuring the instrument. For example, they're measuring its position, because when the molecule hits the measurer, it is kind of recording that there was a thing in its path, which is why it changed trajectory. So the molecules of air and the environment in general is also measuring the apparatus. And how it turns out is that although quantum theory in principle doesn't really provide a preferred basis in an isolated system, the dynamics of a system can pick out such a basis. So the interactions with the environment do pick out a specific basis that the system will evolve in. So, for example, in the case of air molecules, there is position is important, because the air molecules are measuring the position of the measuring instrument, and that will be the technical jargon. That would be it's decohering in that basis. It's decohering in the position basis. So the ambiguity that's there in principle is only there when you don't include more realistic things like there being an environment to the system. And once you include those things, like in a real experiment, then you see that the dynamics picks out a specific basis.
So is it the case that whenever we want to... So you said if the system's isolated, there's no preferred basis, there's nothing picked out. If it interacts with something, and then we do see a preferred basis, and they can go, how do I know what basis is picked out? And then your answer is, I look at how they interacted, and the dynamics of that interaction tells me what basis will be picked out.
Yes.
And so the interaction, the form that interaction takes, tells you what the preferred basis is, and the preferred basis problem is only ever a problem in the context of this setting where you have a system interacting with something else. It's
it's only a problem when it's not. Well, so I think if there are ways of introducing a dynamically preferred basis. So you can say, there's an interaction with another system, with an environment, and then that picks out the specific basis. And that's exactly the case where you don't have this ambiguity. So that's one way of resolving the problem. Because I wasn't sure before you said, maybe I misunderstood the sentence.
I might have said it the wrong way around.
But we agree on the, So it's like there are dynamic, quantum theory, without the dynamics involved, I think that doesn't have the property of there being a preferred basis or observable that was measured by a measurer. And that's not so much a bug as it is a feature. So that is some of the magic of entanglement that can happen. That there is for isolated systems, you can't really say, well, this thing was measured rather than another thing, but you can as soon as there is something else, like the environment, doing that for you.
But what if we're in an isolated system and there's if the whole universe is an isolated system, then you no longer have a reason to have a preferred basis, right? Because you said isolated systems don't have a preferred basis.
Yeah, in some sense they don't. I mean, even in the universe at large, I would still say that if you've identified the environment, so it's true that if you include the environment again, so I think that's what they call purifying, isn't it? Then in some sense, there isn't a preferred basis anymore. but we have a theory of what the environment is and how it's interacting. So it's a system that we don't control. It's something other than the measuring instrument. It's like the molecules of air, and we have theories about what those things are. So we can kind of, in the closed system, we can still identify that, and we can still see branching going on. So the branching is real, even in the closed system. You can still see the branching happening, definitely.
So is it kind of like, they can imagine we have this overall closed system, but then you can kind of look at it as subsystems and look at the interactions between them, and then say, okay, I can see that there will be a certain basis picked out, because if I separate it into these subsystems and look at how they've interacted, then that interaction will lead to this basis being picked out.
Yes, I think so. I mean, the models of it, of course, the models are always the other way around, where you start with, here is the system in question, and then you kind of artificially say, okay, well, that's a system, and what if we included an environment?
Yeah.
So you kind of already know what the environment is in the model.
Yeah.
But I think what you're doing, what you're doing is more realistic in the sense that, you have a system which is a closed system, and then you're trying to determine what the environment could be. Which I think you can still do the same thing. The important thing from my point of view anyway is that when you include an environment, and again you have a theory about what the environment is, it's the uncontrolled part of the system. So molecules of air or photons coming in or things like that, then they pick out a specific basis. And I think there might still be, like, even in the absence of that, I think there could still be a sense in which a basis is preferred. So if you imagine a quantum computer, that is a system which almost by definition doesn't have decoherence. And I think there is still a sense in which there is a preferred basis in a quantum computer, at least at certain times. So it's like there's a way in which information is being processed. The solution that decoherence offers you is kind of to say, due to the history of the system, there is a preferred basis. Due to the way that systems are interacting and their history, you can pick out a basis that the measurement happened in. And although there is no decoherence in a quantum computer, I think you can still do something similar where, for example, information is being used by the computer in a certain way rather than another, and that again gives rise to some kind of history and a basis that is preferable over other ones in the quantum computer.
That's interesting. Like information-induced decoherence in a way, rather than like environment-induced, or in a way algorithmically defined decoherence, because it's
like if you think about the thought experiments of AGIs and things running on quantum computers, which you've done videos about.
Check out my videos.
Yes. That's going to be a link.
But in general, the idea is simulate an observer on a quantum computer, simulate an observer measuring a quantum system, and then try and reverse it. And this is aimed to test whether an observer measuring a quantum system causes it to have an irreversible collapse or a reversible measurement. And the motivation for doing it by simulating them on a quantum computer is that if you try to do this kind of experiment with a human in real life, it's going to be extremely technologically difficult and maybe even impossible, whereas the simulation on a quantum computer seems a bit more feasible, although we still don't know how to simulate AGIs on artificial general intelligence, so something that's like an observer on a computer. But yeah, so that's the idea. And you're saying about if we think about those thought experiments.
Yeah, so the thought experiments are about quantum computers. So the person being simulated in that case is not experiencing decoherence.
Mm-hmm.
He is he's in a coherent state. So that's just to say he's not experiencing decoherence. He's in this situation where you think, well, now there's the preferred basis problem again. But what will happen in practice, I think, is that he will have some definite history. So what definite history? He will have some history in which information is being processed by his brain in one basis rather than another. And that again picks out a basis on the basis of dynamics. So there's, and I think the thing that unites it all is it's always dynamics that picks out the basis. It's not anything else in quantum theory that can do that.
Mm-hmm.
So that kind of relates to your question of how does it work in closed systems? Because this is an example of a closed system. You can still say that there is.
Yeah. It's a good thought experiment to think about. I think the what happens in a quantum computer idea, because if you can, because like you said, like the whole point of a quantum computer is that everything's coherent. So almost by definition, you're not in the situation of decoherence, because decoherence is only when you have something out of your control.
Yes.
Whereas, in a quantum computer, everything is coherent, everything is within your control because it's a computer. Yeah. But you're saying even then, there's a sense in which you can get, for certain situations, you can get a preferred basis being picked out from the dynamics.
Yes. Yeah. So again, there's the dynamics tells a story, and that story doesn't happen in all the different bases. Basi. What's the basis in all the different bases? That's a struggle there.
Bases.
Yes. Mm-hmm. So the general answer is, I think, that the dynamics is the thing that picks out the basis.
Mm-hmm. Right. And so do you find this satisfying? You're happy? Preferred basis problem solved?
I think so. Yeah, I mean, I like decoherence. The thing I like about decoherence is that for one thing, I don't really see the need for it if you don't think there is only unitary quantum theory. So I find that kind of intriguing, because lots of people seem to be on board with the program in some way. So that's not, like, decoherence is not a term that only many world students will use. But I find it intriguing that it's gotten quite popular, but I don't see the need for it if you don't think that quantum theory is only the unitary part. So that's intriguing. It's kind of like a footnote on our physics cultures. Why do we even think decoherence is necessary in the absence of quantum theory being only unitary?
Yeah. So if someone thinks that there is the reversible quantum evolution plus irreversible measurement-induced collapse, then decoherence, this thing where you become entangled with the environment that's out of your control, and then you lose your quantum coherent superposition, isn't, that whole story doesn't need to be, doesn't work anymore, because the whole point was that measurements have a different dynamics where they have this irreversible collapse. So decoherence isn't, there's no mechanism of decoherence, because you either have your coherent thing or your measurement-induced collapse thing.
That's what I would think anyway. I mean, maybe people have like hybrid versions of it where there's decoherence and then there's a domino effect of collapse that happens because of the decoherence that has entangled lots of systems. I don't know. I'm trying to think on the spot of like a reasonable defense of this position, but at any rate, it intrigues me that decoherence is so widely used, because it seems people like Simon Saunders really developed it with that idea in mind, of it being a solution to preferred basis problem.
Mm-hmm. I mean, I'm on board with it as well. So I need to. We could throw it as a question for the audience. If anyone does want to defend the position that you can maintain an explanation for decoherence in addition to some kind of measurement-induced irreversible collapse, and that these are they play distinct roles in your view of what's happening in quantum mechanics, let us know in the comments, because it would be interesting to discuss or to know what you think. Yeah. Cool. And it's okay if you don't, but are there any papers that you think nicely explain how the preferred basis problem is solved, kind of along these lines?
There's a paper by Zurich, which is very good. I don't remember the name of it, but it's a thing which I could look up and I could share in the link in the description or something.
Yeah, that'd be nice.
And which is that's basically about the dynamics picking out a preferred observable basis, and there is David Wallace's book, The Emergent Multiverse, which has a chapter on exactly this. So I thought both of them were insightful, and reading either will help you read the other. And probably David Wallace's book is slightly less technical than the Zurich paper, but both are readable. They're both pretty readable.
Cool. I'll put links in the description.
Cool.
Yeah. Okay. So now there's another problem that is, I think it's interesting. It's not one that people in the technical quantum community seem to worry about much, but whenever I talk to people that aren't kind of studying quantum foundations, it's a question that they come up with a lot regarding the many worlds interpretation, and that is, how does it reconcile with conservation of energy? Because when you imagine this multiverse where everything's constantly branching, it seems like everything's constantly being duplicated or replicated, or
right. Oh yeah. Where's the mass coming from?
Many this whole branching of loads of versions of everything, and that seems kind of in contradiction with conservation of energy, because how are you able to make so many versions of everything? Everything is as equally real, solid as everything else. So where's all this stuff coming from?
So there's a somewhat easy solution to the technical problem there, which is that energy is a very straightforwardly a conserved quantity in many worlds, just because everything evolves unitarily, and unitary evolution gives rise to conservation of energy in a straightforward way. If anything, I would guess that collapse does not preserve energy. I'm not sure, but it depends on the basis, I guess. So if the thing that is being observed is compatible with energy being conserved, because if it isn't, then kind of a hedging there. But anyway, in many worlds it is straightforwardly energy is straightforwardly conserved because of unitary evolution, and then the question of why is it that seemingly matter can come into existence? I would say it's kind of already there. There is, I guess there's not really an agreed upon answer to that question, not one that I've seen, but the best I could do is something like there are just, before branching happens, there are lots of different versions of you already, but they are all exactly identical to each other, and then some of them become different. So if they're already there, then no matter had to be created to make them different. So that is, that's my simplest answer, I guess.
But if
it's not very satisfying with the answer.
if all these future selves are already here, then shouldn't it be like really massive? Like if there's not like any more mass here than.
Also, again, I haven't really seen like one specific take on this, but the way I, for instance, heard Deutsch talk about it is just there are already these instances, they already live kind of next to each other, all being the same, so they're not here in the sense that they're all clustered around us or something, but
they're in the quantum space.
Yes, something like that. Yeah. And then at some point some of them become different. Mm-hmm. So if they're already there and then they become different, then you don't need to create any mass or destroy any of it. It's all there already.
Yeah. So it's almost like there's like a bunch of meanness, and then sometimes parts of it become different, and it's like there's no limit to how much you can keep dividing the meanness in a way.
Yeah.
Like it can keep, as the further branching happens and things that were the same become distinct.
Yes.
They can keep kind of becoming distinct without any limit to how much they can keep kind of branching.
Yeah, I know what you mean. Yeah, this is one of those ways in which quantum theory balances the continuous with the discrete, because states always change continuously, and the reason why they do that is because like there's some measure for how much of the state is in, words kind of fail me now, but how much, for example, how much of the state is in one state is a great thing to say. But you can say, let's say you have a qubit.
Yeah.
You have a qubit, and the qubit can be in state 0, or it can be in state 1, or it can be in both at the same time. Mm-hmm. And it can change continuously from being, for example, just 0 to being 0 and a little bit 1. So you can gradually make whatever the state is initially into the superposition of 0 and 1. Mm-hmm. And the discrete bit is, it can be 0 or 1, and the continuous bit is, it can also be a superposition of those, and it can move continuously from it being just a 1 or just a 0 into it being the superposition of 0 and 1. Mm-hmm. And there's a measure for how much of the qubit is in the state 1 and how much of it is in the state 0. Mm-hmm. And I think that measure is kind of like saying how many instances of it are in this state versus the other. So that's why I get the idea that there are already many instances, and you can turn some of them into, for example, the one state, mm-hmm. in a gradual, continuous way.
Yeah.
In such a way that the measure of all of them is still conserved. So you still have, like, if you add up all the bits of the qubit being in state 1 and in state 0, then they always add up to what they were initially. And this is how you can still continuously change between discrete states. Mm. So that is, I think that would also be true for things like energy conservation, where you don't actually create new energy. It's just some of the things that are already there continuously change into other things.
Mm-hmm. Yeah. And is there no limit to the gradation along this continuum that you can do as you go from 0 to superposition with more and more 1?
Yeah, I mean, if the time step is incredibly small, then you have created an arbitrarily small change in how much of the state is 0 and how much of it is 1. Mm-hmm. So in principle, there's no limit on how small that can be, just because of our equations of motion being continuous.
Mm-hmm. Yeah.
Yeah. yeah, it's a little bit. I've not really seen any of that discussed anywhere.
Yeah.
But that's the only way I can really make sense of the of these coefficients in the state.
Yeah. Yeah. I think it's an interesting point that I always find it interesting that no one worries about this in the technical community, but like everyone worries about it, or a lot of people worry about it in the non-technical community. And I think it's because of what you said, that you can really straightforwardly see from the maths that energy is conserved according to our technical requirements for energy conservation. But if you're just thinking about it, like the branching, it's like,
what's going on?
Oh, someone told me that it's branching into like that seems to just violate this principle straight off. So
yes,
it's interesting to discuss that merging of how to get the intuitive understanding out from the from the maths. But I think you explained that nicely.
I think there's also a slightly separate issue where people sometimes think that energy conservation is only true at the level of the expectation values, where
averages.
Oh yeah, sorry, yeah. Like technical jargon is so ingrained.
Just like average values of your measurement outcomes when you measure the system.
Yes.
Yeah.
Yeah, that it's so you can kind of see that sometimes people think you can see a violation of the energies in specific. You don't see them on average, but you see them in specific measurements.
Right.
So like sometimes it deviates, but then if you can measure something in one energy level rather than another, and that is supposed to be fine because on average you see that energy is not. The average is still conserved even though any specific measurement is not. I think that also is not, that is not true. It's also conserved in each branch, so it's not like you can accidentally create a violation of conservation of energy within a branch just by being lucky, basically. That also does not happen. I think Chiara and Flatko had a nice paper about that.
Yeah. Our supervisors.
Yeah. Chiara Miletto and Flatko Vedrol had a good paper about that.
Yeah. But that one is quite a subtle point that a lot of people in the research community would have this impression that energy is conserved on average rather than per branch. So it's an interesting point it's interesting to just go through it yourself and check that energy is conserved branch by branch and convince yourself that is true. Yeah. Cool. So now I have a question that does worry the research community quite a lot, I think. And it's maybe not so discussed in this context on the more popular level, but this is on the first podcast episode of this series we discussed the issue of locality with our other alumnus from the group, Nisetu Tabavada, and we discussed how to explain entanglement in a way that's fully local, which means that there's no instantaneous action at a distance at all, contrary to popular discussions of entanglement and this whole idea of non-locality having been demonstrated by Bell inequalities. But and this issue of locality kind of pops up in a different way when thinking about many worlds, because you might think that this branching into many worlds is violating this fundamental principle of locality, of no action at a distance between separated systems. And so if I'm imagining that I've got my world and then this measurement happens and someone's measured a superposition of 0, 1, so now one version of them sees 0, one version of them sees 1. Now, if I've got this massive world that has a big spatial extent and then it's just split in two, then hasn't that violated locality?
Yeah, I mean, because the whole world splits.
Yeah.
Yeah, I think that would violate locality, but that's not, I don't think we should describe it as such. That the way in which I think it should be described is that the branching happens locally, and it kind of grows like a bubble. So if you look back in time, you can see the systems that have been affected by the measurement, or over time rather. But at any instant, if you perform a measurement, the only thing that affects is the system being measured and the measurer, and nothing else. So yeah, if you're committed to having the branches be actual complete worlds, so that it's everything in the universe, then yes, you have to say that there's a kind of non-locality in theory, because the world itself is just everything that exists, meaning that if you do something here, then you automatically end up creating these two separate complete universes, which are not local in the way you're just describing. And I actually wrote a paper about that, in which Deutsch and I described how you can resolve that. And then after having written the paper, I found another paper by Paul Robichaud, which basically does the same thing, funnily enough, but in a more general setting of non-local boxes. And the thing that he does, and the thing which, in hindsight, Deutsch and I did, was that what happens during a measurement, for example, so maybe this is more specific, but this is, if you have a bell-type experiment where I have, we have a shared state, I measure part of my state, and then I think, oh, well, because I have seen my state, I can now say what's going on with Maria's part of the state.
Well, we share an entangled pair.
Yes.
Yeah.
So the common view, the view you just described, would really say, okay, we perform the measurement, and then there's a world, and then in one world, both your outcomes are a certain way, and in another world, both your outcomes are another way. And that's the same non-locality that you were describing, of the world really splitting in two. And the way that, so kind of Paul Robichaud and Deutsch and I did it separately from one another, was to say, well, what's going on is instead that you perform the measurement locally, and then you split into two versions. And so, for example, I perform the measurement and I split into two versions. You do the same thing with your part of the state, and then you split into two versions. And when we meet up, there are rules for which versions of us can see the other ones. So the version of me that, for example, saw a 1 can only see the version of you that saw a 1. And the version of me that saw a 0 can only see the version of you that saw a 0. But the only thing that's happening is that I'm split, or I branch locally into two instances, rather than all of that happening simultaneously. So, for example, if you were to perform a different measurement, a measurement in another basis, or a measurement of another observable, to say the same thing, then I wouldn't be able to tell that, and I can't see that you've done that from my description of both the state and myself. And yet, there will still be similar rules for what we can see, or which versions of us can see the other versions of each other, despite that. So it's you can do things locally, and it won't affect the other person. It won't affect the description of the other person. And the nice thing about it is, because of these rules of which version of us sees which other version of the other, the whole thing works out in a local way. So you kind of have these local bubbles of stuff happening, and then kind of the bubbles grow over time, rather than these being complete. Like, it's not everything in existence that suddenly splits.
Right. So me and you do our measurements, say, representing us by figures, and then we each split kind of individually. So you, when you do your measurement, me when I do my measurement, And then when we compare our measurements, our branches kind of know which one to match up with.
Yes.
And that's when they kind of merge into the world where we both saw 0 in superposition with the world where we both saw 1.
Yes, yeah.
How do our branches know to match up correctly?
That's a difficult question. It is, again, it's the dynamics. So the dynamics lets some parts of us interact with other parts. So like I can, that sounds not good. Okay, so the dynamics is the thing which determines that, I think. And it's that some parts of the state can only affect other parts of the state. So hang on. Got slightly flustered there.
Maybe we can skip it, but
No, it's a nice
I've been
question.
asked this a lot when I talk about this.
No, I think I can answer the question. I should be able to
Not
recover
for the
it.
challenge.
Yeah. Okay, so I think the answer to the question is that the dynamics of quantum theory has that baked into it. So there are rules for which part of a quantum system, or of which instance of a quantum system can see which other instances. And it's something like that the rules of quantum theory do the following. For example, if one system is in the state 0 and another system is in the state 1, then a certain interaction will happen. So maybe that part of the state will turn into 1, 1. And if one system is in state 0 and the other system is in state 0, then they will both turn to 0, 0, so nothing will happen. So these are rules for what happens on specific instances or for specific states, and the same rules apply when there's a superposition. So by having specified what happens in these two situations, you have strangely specified, that's kind of the magic of unitary evolution, you've also specified how the evolution happens in superpositions. And that is also what happens with these instances, that parts of it will interact one way because of the state of the one system, and then other parts of the state vector will interact another way because of the state of the other system, and these things kind of happen separately from each other. They're dynamically isolated. Mm-hmm. So I think that's my best attempt. It's a hard question to answer, but it comes down to the rules of quantum theory applying to specific bits of the state vector, and then generalizing to superpositions as well.
Mm-hmm. Right. Yeah. Okay, so we've solved
Us personally, right here.
right here.
Yeah.
We have solved probability, preferred basis problem, conservation of energy, locality. It's quite a strong list. So I guess it's now interesting to talk about what we do next. So we've talked about all of the things that make sense with many worlds, but is there anything that doesn't make sense?
Well, I think it clarifies some of the other problems that we have with physics. For example, we want to unify quantum theory and gravity, and I always found the usual explanation of that kind of strange. Like in the usual way of explaining why there's a need for quantum theory of gravity, you don't really get the point. It's like the usual argument is something like our normal model for how forces work, how the standard model of fundamental interactions is a quantum theory, and the only force that's not like that, or the only fundamental interaction that's not like that, is gravity. So we should maybe want to turn it into a quantum field theory or something. And the way I like to think about it is instead that you can make a much stronger case. Instead, that's kind of sanitized, but you can make a much stronger case for why you would need a quantum theory of gravity if you're many worlds, just by saying, for example, the Earth is a quantum system. It consists of atoms and things like that, and therefore, there's some quantum description of the entire Earth and everything on it, as it is orbiting the Sun. And in different branches of the multiverse, the Earth will have very slightly different positions, and so will the Sun. And so the gravitational field, the space-time, will be curved slightly differently in those different branches. But in our best understanding of general relativity, there is no such thing as space-time being different in different branches. Space-time has a definite value, and yet the argument I just gave seems to suggest it shouldn't. It seems to suggest that it should have different values in different branches. And I think that's a much stronger argument to make. So that's not necessarily a problem with many worlds in particular, but that is, it allows you to see more clearly why you would want something like a quantum theory of gravity. There is a problem of time travel, because, again, that's kind of coming from general relativity. We know that there are places, regions in space-time, such as within rotating black holes, curved black holes, where you seem to be able to travel back in time. And there are models that kind of suggest that perhaps a many worlds approach to that could clarify what happens in those time travel paradoxes, because if you have a single history in which a person travels back in time and has to create a consistent history, then you have things like grandfather paradoxes, like you can go back in time and kill your own grandfather, and then you prevent yourself from going back in time. And so that you can't form a single consistent history of something like a grandfather paradox. But maybe having these other branches allows you to have multiple histories at the same time, so that when you go, for example, back in time, you actually travel to another universe, and in that case, the problem is avoided. So that was a model that Deutsch developed for time travel back in the 90s, I believe. And I think there's still some problems with it, problems with locality, because his model doesn't seem to be local. So then, yeah, there's still open problems in that regard. There are, I think, the way I generally think about many worlds is just that it allows you to not get bogged down with some parts of quantum theory that you can otherwise spend endless amounts of time thinking about. In some ways, I like your paradoxes series, and in some way, I think the solution to many paradoxes is just, well, if you have unitary quantum theory, then actually this is not such a problem. Like that's the issue with locality that you discussed.
Yeah. So for context, this paradoxes series of videos that I made for the KissKit YouTube channel when I was working with IBM Quantum. I made these 14 videos, each taking a counterintuitive thought experiment, mapping it onto a quantum circuit that you can run on a quantum computer, and then explaining how you can run it on there. And I kind of realised, so I was doing this with loads of thought experiments like Schrödinger's cat, double slit, quantum eraser, quantum bomb tester, EPR paradox, quantum teleportation, and I realised at some point that all of the resolutions were exactly the same, which was turning the measurement device into a quantum system and then saying, look, everything makes sense now. And even though, they all seemed very different in storyline, and they do tell you different things, but they all have the same resolution for making things make sense. So I mean, for me, that was very satisfying in terms of, I was like, apply quantum theory to measurement devices, and all of these 14 counterintuitive things just get made satisfied, like with one solution.
I agree. Yeah, you can explain an awful lot with it, which is, again, it's like, we don't have to get bogged down by these issues, and it clarifies lots of things, including the problem I just described, the problem of why we need quantum gravity. It can kind of have it doesn't necessarily provide a solution, but at least it provides a crisp understanding of why you want something like that. And yes. So the question was? The question was...
it was about...
open research, what's still going on. So I feel like lots of the... I think there's still philosophical issues with many worlds, or at least it gives rise to philosophical problems that I don't really know the answer to, like personal identity and things like that. But I don't know substantial physics problems that I would still have with it. It's more that I'd like to use it to do physics with. Maybe an example of that is a nice paper by David Wallace, where he describes the quantum theory of magnets and magnetization using many worlds, and that's always what I imagined I want to do too with many worlds. It's like you have a thing, the normal theory of it doesn't quite make sense. He gave a brilliant talk about it at some point in Oxford, where he said the usual theory of magnets is something like magnetization happens spontaneously when the system is infinitely large, and then he took out a magnet and he was like, yes, not infinitely large. and then he gave a very nice explanation of how you don't actually need the system to be infinitely large just because of decoherence and branching. And I said, that's kind of how I view the whole research project. It's more that it allows you to then tackle these other problems in a very nice way. And there might still be problems with it, there might still be specific issues, like people are still working on locality, and Setu did some great work on that. But there's nothing I would consider to be, like, I wouldn't really necessarily consider that a problem with many worlds, if you get what I mean. Like, there is a problem of locality of fermions, for example. But I wouldn't have said, now in the many world scheme, there's still the issue of does many worlds allow for locality of fermions? It's more, there was a problem with locality for fermions, and then many worlds again gives like a nice explanation of that too.
Yeah. Cool. And is there anything that you're working on at the moment that kind of relates to these ideas, or that you find most interesting at the moment?
So we are both working on a paper on locality, which is fun. Yeah. So that's a nice. I enjoy that. That's, again, it's coming from. We too assume that quantum theory is unitary. We don't. It's not like, again, it's not explicitly a many worlds paper. It's not like we have to say, so we are many worldsers, and we believe in Everett that he solved the measurement problem. But you work with the unitary part of quantum theory, and it is Everettian in that way. I really like a model that explains time, and it's called the Page-Wooders model, which I think is just exquisite. It's very pretty, and it too is a model that works only if you believe in unitary quantum theory, because it gives an account of things evolving unitarily. It doesn't give an account of things evolving on the collapse. And it is, so it's separating in that way, and as Deutsch has pointed out, in the model, different moments in time are like different Everettian universes. So it's related to Everett in that way. But again, the other angle's just, I like the model, and it's unitary, so I don't have to worry about like all the usual problems. We can just work with the model, and it's nice and pristine, and we can do physics. So my my spiel for Everett is very much, we can just do physics. It is nice. We don't have to, like, all these issues which otherwise are distracting are just not there, and it's just it's kind of satisfying. And then we don't necessarily have to keep thinking about what about there being other universes, but it does allow. Well, we could think about there being other universes, but we don't have to. Yeah, the focus with me anyway is not necessarily on that. It's more that we can do physics, we can do interesting stuff because of it.
Yeah, great.
Cool.
So, I think we've. I was gonna say we've covered a good range of topics. Maybe we should wrap up. But there was one more thing that came to mind that comes up a lot in a kind of different context to the other things we've been talking about. But we've mentioned quantum computing a bit, and in case you're not familiar with it, the general idea of quantum computing is that you build computers based on quantum bits, and these can process information using quantum bits instead of classical bits. And for certain problems, we've shown that they could be solved much more efficiently by processing this information on the quantum computer rather than on a classical computer. And in the kind of quantum computing space at the moment, especially on social media and just in general, I keep seeing this kind of debate in a way where you'll get some people saying that the way quantum computers, well, there's a kind of common misconception that the way that quantum computers work is by doing classical computing but all in parallel. And then you'll have people saying that quantum computers work by computing everything in all the branches of the multiverse at the same time and doing all these computations at the same time. And then you've got other people saying, this is the biggest misconception in quantum computing, this is really bad popularization of quantum computing, all this stuff about computation happening simultaneously across the multiverse really doesn't make any sense. We need to stop saying that when we're communicating about quantum computing. So I wanted to ask what you think about how quantum computers are working and how that relates to the multiverse. So are we quantum computing? Are we doing computation across the multiverse? Are things happening in parallel? What's happening there?
Yeah, I think so. I mean, the thing that happens is that you do compute things in parallel in the computer, so that many computations are happening at the same time. It's just not that you can't leverage that immediately. It's not like you can pick out the solution that you want. So if you were to do just parallel computing, so having everything happen at the same time, and then you pick out, or you measure the system, you see if you can find the function that you want to find on the input that you wanted to compute, then that's not going to give you an advantage, because you're just going to get a random answer most of the time, and then the answer you wanted only some of the time. So what you instead have to do is you have to use clever techniques to make the branches interfere with each other in such a way that the bad answers kind of go away and the good answers become more prominent. But yeah, it is a key aspect of it that there is things going on at the same time. So you do compute, for example, the answer to a function in all the different branches, and then you try to do clever tricks to make sure that the branches that you don't want to be there kind of don't get amplified, they get diminished a bit, and the branches that you do want to be there get amplified. So both are really key aspects. If you don't have the things going on at the same time, then you don't really have an explanation of why you need the latter bit where you are trying to extinguish the bad solutions, because they are there and you just don't want to see them. So yeah, I think calling that the biggest misconception. I mean, I definitely agree we should include the part about interference and how we get the actual solutions, but it doesn't contradict that things do go on in the quantum computer at the same time. Like, you perform many different calculations at the same time in the computer. You just have to find non-obvious ways of leveraging that. So
yeah, so there's some truth to the idea with this kind of caveat that you need to include this reinterference part, which is a really key, difficult part of making quantum algorithms actually do anything interesting.
Yes.
But it is also making use of the power of the quantum multiverse in
definitely. Yeah.
Getting the computation out in a more efficient way than classical computing can.
Yes. Yeah, again, the video we mentioned before, the one about that you made about an AGI running on a quantum computer, there will be a definite experience that person being simulated has, and the whole point of the experiment is that you can see there was another version of him. So if you buy the assumptions of that experiment and you think that the person is really having two experiences at the same time, each in a different branch, then the same should be true just generally. That you can, like, that is a specific example of some kind of computation happening in the computer, and more generally, you can have such branches with many different kind of computations happening at once as well. So yeah, definitely there are, if we're able to build a quantum computer, that we will be using the multiverse to compute things that we otherwise couldn't compute with classical ones, just because there are different branches in the computer that are calculating different things. And then there's the caveat, and we have to make them combine in such a way that we have to be clever about it, but that doesn't negate the previous part, that they're both true.
Cool. Well, I feel like that's an interesting point to wrap up with.
Cool.
So, yeah, I guess just to kind of summarize what we've talked about, we started off kind of introducing the idea of what the many worlds theory is. Why do we need an interpretation of quantum mechanics? Why can't we just carry on the shut up and calculate with, as people say? Oh, that was another thing I wanted to ask. How would you respond to people that say we should just shut up and calculate and not care about interpretations of quantum mechanics?
Yeah, well, they should do that. That'd be nice. Yeah.
It would be nice for the shut up and calculate people to shut up and calculate. But
I'm going to offend lots of people.
So we talked about why you need interpretations of quantum mechanics and the various issues that people have with it, both on the kind of technical side and like intuitive side. So there was this issue of absurdity, it just seeming really bizarre, and then there's probability, where you discussed various derivations of where you can derive the Born rule. The preferred basis problem, where you get this kind of unique property that you're measuring, how to make sure that you get one property being picked out despite an ambiguity in the way that you can write out the quantum state. And we discussed solving that by having a property picked out by the dynamics. And then we discussed the issue of conservation of energy, which it kind of seems like branching doesn't conserve energy, but when we write it out technically, we see very clearly and simply that it does. And you gave some intuition for why that's the case. And then we discussed what did we discuss after that? Locality.
Locality, yes.
Locality, how you can explain branching in a fully local way. There's no action at a distance needed for branching. And open problems that, not really with the many worlds theory, but that it can be applied to solving or that haven't been solved yet. Like things to do with time travel, for example. And then quantum computers, whether they work using the power of many worlds, where your answer was yes, they do.
Yes.
Yeah. And that was our conversation.
Yeah, it was great. It was really fun.
Yeah.
It was fun chatting.
Great. So thank you for joining us for this many worlds discussion in this branch of the multiverse.
Hopefully many others.
Hopefully many others. Hopefully in all the branches of the multiverse in all the ones where this podcast exists, you also joined us for the podcast.
Indeed.
And I feel like we should have done some kind of like live quantum measurement to like make two versions of the podcast for like different branches of the multiverse.
Yes.
But it's really fun. Anyway, I'm sure that there will be deviations of different versions of this in different multiverse branches anyway.
Yeah. There's gonna be natural deviations.
Yeah.
We don't have to make them happen.
Mm-hmm.
It's enough that we know that they are there.
Mm-hmm.
Like we learned that they're there. There are different versions of this podcast. There's different versions of us and everything, and that's enough.
Mm-hmm.
We did our part in explaining it.
Mm-hmm. Okay, good. So, and please join us for more episodes of the Quantum Foundations podcast. Don't forget to like and subscribe.
Very nice.
And I'll put some resources in the description. Please comment if you have questions or feedback or comments. Always happy to hear them, to read them, and maybe respond if I have something useful to respond if it's a question. Then I will do my best. And thank you, Sam, for joining today.
Yeah, thanks for having me. It was great. Very fun.
Great. Okay. Bye.
Blah.
Blah blah.
Blah, 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 blah.
Blah 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 blah.
I think it's really weird when people say blah, blah, blah.
Yeah.
They really should not do
They
that.
really shouldn't do that.
Yeah, it's embarrassing.
Yeah. Mm-hmm.
Blah, 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 blah.
Blah blah blah.
Blah, 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 blah.
Blah.
Blah, blah.
There's probably a branch of the multiverse where we did that. But
But the whole language is just blah, blah, blah.
blah 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 blah.
Blah, blah, blah.
Yeah, who would do that though?
It's strange.
Yeah. Blah
Blah,
blah.
blah.
Mm-hmm.
Lots of things can happen, but that's too strange.